Okay, let's start. So we are at the final chapter already, which is called feedback. Okay, so after this chapter, next week I won't be around. I'll be going Taylor's University for a talk. So I will see you guys next week only. So this is week 10, right? 11, 12. So I'll see you guys week 12. We can have our quiz on week 14 maybe. So week 12, the whole day, so the whole class will be about revision for the quiz. Okay, so I'll tell you all what to study, give some examples, and that will be the revision for the quiz. Right? So from this chapter, hopefully we can finish up today, maybe. Let's see. If cannot, we will finish week 12 as well, and then we do revisions. Okay, so before we go into feedback, we need to get a bit of concept before going into what exactly are negative feedback, positive feedback. So first of all, when we see voltage source, we say that voltage source, ideally, it is just a voltage, and then the resistance of it is 0. Basically, it can push through everything very nicely. So the resistance of it, ideally, it is 0. However, we know that nothing is ideal in engineering. So there is always a very small resistor in series with the voltage source. Similarly for current usually, we say that we want to pump a very high current in. Okay, so only my path I want to have current, other path I do not want to have current. So usually current inside of it has very, very high impedance. So the R is basically infinity. But in real life, we cannot do that. So in real life, there's actually a very, very small sum R out that in parallel with the current source. So when current actually going through, it needs to go straight, but sometimes it will split some current to the other side because there are some resistor other side. So that's the general idea. So voltage, this is about sources. The next one is about voltmeter, ammeter. We know that when we design voltmeter in instrumentation, ammeter in instrumentation, we use galvanometer, and then we will, for voltmeter, we will have a multiplier resistor in series with the galvanometer so that we can tune to the range that we want. So that's voltmeter resistance. Ammeter resistance, usually when we want to connect our ammeter in series with the circuit, so we hope that this ammeter will not consume any of our power. So ideally, this ammeter is supposed to have 0 resistance. And voltmeter, suppose internal resistance should be very big so that all the other current can flow to other side, not to the voltmeter. So that's the concept. So you can see they are basically in reverse way. As a voltage source, resistance is 0. As a voltmeter, when you want to measure, it is infinity. Current source, resistance is infinity. If you want to measure current, resistance is supposed to be 0. So this chapter is about feedback, but why exactly do we need feedback? We say that gain is equals to negative GMRD all the time. GM itself consists of mu n C ox, temperature, process, VDD, everything. So they are very PVT dependent. Process, temperature, voltage source. So all these things might lead to some non-idealities. So we want to try to cancel out any way that we can cancel out the A, so that we can straight away use other circuit to compensate the gain and stuff. So that's why we need a feedback system to know what exactly happened. We compensate back. The feedback system that we'll be using is only negative feedback system. Usually around the world, nobody uses positive feedback system, or very, very rarely. We want a negative feedback system because we'll be getting something that is wrong. We cancel out what is wrong and then get the correct one. So generally, you will see this diagram a lot. X input go in. We have subtractor. Then go to our main amplifier. The A is your amplifier. And then go to output. That's the general single op-amp or something. But if you want to add feedback from the output of Y, you will need to have another amplifier or another circuit as a K, and then loop back to your input. So that's for your feedback system. So we can call the input as X, amplifier as A. The amplifier, we can just say is a feed-forward circuit because it feeds through to the output. Output is Y. For feedback, we call it K. And then maybe here we say this is U. Okay, so we look part by part. Error signal. So what exactly that is wrong? Because initially you should be getting some ideal X, but you get Y. So you add your Y, go back to here, you minus out X minus the output from your feedback. You get what is wrong. So that's your error signal. So X minus U, this line, is your error signal. For feedback signal, feedback output is your U. Okay, you can just go step by step over here. So feedback output is your U. What exactly is your U? U is this K. Feedback times with output Y. So Y times K equals to U. And K is your feedback factor. Like, what's the skew? It is in terms of, it is unitless. Okay. So we see part by part. First, we go through first block. What exactly is our A? We can say A is X input minus U. What we get from A, from this side, is X minus U. Then only we can get the input of A. What exactly is Y? Y is A multiplied by whatever happened in front. Whatever happened in front is your X minus U. So we can say Y is equals to A times X minus U. Then what is your U? U is K times Y. So we go part by part. Input of A is X minus U. Y is A times X minus U. K, you will get output input of Y. So the output of feedback will be K times Y. Then we can substitute the value. So what exactly is Y? Y is A, X minus U. So Y is A, X minus, what is your U? U is Y times K. Y times K. Then you multiply inside the A. So in the end, you get this equation. But from this equation, we want to find out the gain. Basically, the gain is what we call the closed loop gain. Because now this is a closed loop system. If you only got one amplifier, this is open loop gain. If you got the whole closed loop system, this is what we call closed loop gain. So we want to find output over input, Y over X. So Y over X is equals to A over 1 plus Ka. From this term itself, you can see A is open loop gain. Ka is what we call loop gain. Ka is loop gain. I will explain what exactly is loop gain later. And the whole green term, the whole term is closed loop gain because we derive from the whole closed loop system. Okay, you can have a look at this part first because you need to understand this part before we can proceed to many different types of feedback system. I'll give 2 minutes. Okay, next part. So you realize that from this whole equation that we derive, closed loop gain is the whole thing. And open loop gain is just the A. You realize that closed loop gain overall, it will for sure be always smaller than open loop gain. So that's the bad thing about feedback system. you will need to reduce your gain. However, when you have feedback, the whole PVT dependency, the reliability increases. Okay, so maybe we can tune our loop gain a little bit so that the system will not degrade so much, will not attenuate so much. So we can observe a few things. Okay, I just copy this A divided by 1 plus A, Ka down there. So we will see from here. So we can see that if our error reduces a lot, if our error is very, very small, means that our X is very equal to U, then it is a well-designed system. The second thing that we can observe is if our loop gain, our Ka is very, very high. Basically, we can ignore the 1 plus already. So we left with A over Ka. Then we can cancel out the A. So our gain is basically 1 over K. So everything depends on only our feedback transistor, resistor, or any feedback circuit. So in this way, we cancel out all the independency of the GM already because we left with 1 over K. So how do we make our gain very high? We just make sure that our K is lower than 1. Then there's gain already. So that's good enough. Now let's try to find open loop gain. So open loop gain is our A, right? Open loop gain is just our A. So if you have a very closed loop system now, it's already a feedback system. How do you find the gain? The open loop gain? Basically, you just break any part of it. Break until you just get X, A, Y. And then this K, it is not connected over here. It is floating. So you can just find what is your X over Y, then that is your open loop gain already. That's very straightforward. But what if you want to find loop gain, Ka? Loop gain is Ka. How do we find loop gain? We have to follow this step. First, we set all the source to 0. We ground all the sources. Okay. Then second thing is we will break the loop. You can break anywhere you like. And we will apply one V-test. And then we will let the part that is broken to be VF maybe. Okay. So final is we want to find out what exactly is your Ka. So let's go part by part and see. This is our closed loop system. We break some part of it. Okay, we just break this part. We apply a V-test. So let's examine what is your VF. Okay, VF. Let's go. We see V-test times K is somewhere over here. V-test is positive times K is V-test K. But after we go in here, we got negative. Here we got negative. So we say that whatever input over here is X minus this. X minus this part. Okay. So basically it's X minus your K V-test. But X now is 0 because we say we want to ground all the source. So here is basically 0 already. 0 minus K V-test. So it's negative K V-test. And then what is your Y? So VF is actually exactly at your Y, right? If you just move up, it's exactly at your Y. So Y, it will be negative V-test K times your A. It will be your VF already. So the formula to find loop gain Ka, the formula is negative VF over V-test. Negative VF over V-test is the formula, the one that I highlighted. So you check VF over V-test. You move this down. So that's your loop gain, Ka. Similarly, I say you want to break anywhere you like. So I don't want to break at the front part of my feedback. I break at the back part of my feedback. I test and see whether it is still the same thing. So over here, it is your V-test. Go in, it will be negative V-test. So negative V-test times A times K, it will be your VF. So similarly, negative VF over V-test, negative VF over V-test, you move down, it is still equals to Ka. So that's how you find your loop gain. Okay, we look at one example over here. So we have our gain to be 100, open loop gain to be 100, your feedback to be 0.1. And we already know that Y over X Our open loop gain is 100. Okay, very good. Then our closed loop gain is A over 1 plus Ka. So we substitute the value inside, we get 9.09. Okay, so looks like, oh, my gain actually degrades by a lot. You can see this part initially is 100. Now my gain degrade by so much. So that's the bad part of your closed loop system. However, what if suddenly my open loop gain changed to 50 instead of 100? So it changed to 50. Let's try and see, change this formula to 50 as well. This A we change to 50 as well. Then now it becomes 8.33. So you can see the difference. Open loop gain, it can drop from 100 to 50, but my closed loop gain is very stable. No matter how you change your A, it won't affect me too much because it depends mainly on my K. That's why when initially maybe it is dropping, but some system doesn't have so much of gain, so that's still okay. Maybe it's dropping to 9.09, but it is very stable. No matter how you tune your amplifier, my gain is still 8.33. So it only dropped by 1. Instead of drop by 50, it drops by only 1. So that's the good part of feedback system, reliability. Okay, let's look at the second example. So this example actually looks like your op-amp system. Okay, so we can have a look at this whole thing. We can say that this whole thing is basically A x minus U, because the output of here is A times x minus U. So what exactly is A times x minus U? Basically, it's a gain, but it amplifies the difference between two parts. So this looks exactly like your differential amplifier that we learn probably in instrumentation, year 2, year 3. So this is exactly your differential amplifier already from this block itself. We can actually convert it into a non-inverting amplifier. Okay, differential amplifier, the one that we learned, we say that, oh, we can put resistor in front, and then one feedback resistor, and then one more resistor from U to ground. So that's my differential. So let's say I take this black box, which is this differential amplifier, directly into this black part. And then I add. So I know this part is negative. So it's my U. I add 2 resistors over here. Then this looks fully exactly like your non-inverting op-amp already. For non-inverting op-amp, we know that the gain is equals to 1 plus R2 over R1. So this is exactly the same thing. We can examine and see. We know that X over Y for a closed loop system, this is a closed loop system. This blue color system and this green color system, they are exactly the same thing because we just model them differently. So this closed loop system is equals to A over 1 plus Ka. We know that generally closed loop system is this one. U is equals to K times Y. That's generally what we know. But what exactly is U now? U is a voltage. So at this point, this voltage, can we say that it is actually R1 over R2 plus R1 times input where Y? This is just a voltage divider over here. So we say U is equals to R1 over R1 plus R2 times Y. What exactly is your K then? What exactly is your K then? We say U equals to K times Y. Here we got Y already. So your K is R1 over R1 plus R2. So now you already know your K, you know your A. You can substitute everything inside. A over 1 plus your K, A. So now the whole thing, we assume that our K is very, very big. We cancel out the 1. So you, in the end, you can get your Y over X to be 1 plus R2 over R1. So this is exactly what we have learned in non-inverting amplifier. So we say that if temperature varies, as R2, R1 ratio is still the same, both will have the same characteristic on temperature, then the gain can still be maintained. Okay, so that's the good part for feedback system. Okay, let's look into, so again, we haven't gone really into feedback system. But let's look into why we need feedback system. So what are the good parts of feedback system? The first good part is gain desensitization. So means that we don't want our gain to be so sensitive. So sensitive. So for example, just now we already did the example just now. Our open loop gain is very sensitive. So we want to control the system so that it is not so sensitive to gain. We use feedback. So the first point is we try not to let the system to be so sensitive to gain. The second one is bandwidth extension. Bandwidth extension. So normally we know we have learned the last week. Bandwidth of a system generally for transfer function. We say that it is A over 1 plus S over omega P. So it depends on how many poles you have and stuff. But if we consider this whole thing as just a closed open loop gain, this is open loop transfer function. So we call it AS. Then the feedback network in terms of frequency response, it will just be AS 1 plus KAS. So what exactly is AS? You plug this whole thing in, A over 1 plus S over the omega P. You plug this whole thing inside this AS as well. So it becomes this. So you rearrange, you get A over 1 plus KA plus S over omega P. Can rearrange again, you get A over 1 plus S over omega P. So what you can see over here is, what you can see over here is the gain, initially my gain, supposed to be A, the very big A. So the black color one is my open loop gain. I only got one block open loop amplifier. So that's my gain. But after I derive everything to consider frequency response, this looks like my final gain. A over 1 plus S omega P. This becomes my gain. Okay, this becomes my gain. So what exactly is this thing? 1 over 1 plus K. This is my closed loop gain. Bottom is also my closed loop gain. So looks like my gain change from A over 1 plus S over omega P change to A over 1 plus Ka divided by 1 plus S over something omega P. So my closed loop gain now it becomes A over 1 plus K. A over 1 plus K. So the whole gain drops down. But what happens to your pole? My pole initially is just omega P. But right now, my pole is something times with omega P. 1 plus Ka multiplied with omega P. So omega P, initially the gain, it was very close to low frequency. But now because I multiplied with 1 plus Ka already, the whole term multiplied by 1 plus Ka already, the gains, the bandwidth seems to be moving to the right-hand side. Although the gain lower, but the bandwidth moved to the right-hand side. So the second point of bandwidth, second point of feedback advantage is we got bandwidth extension. Lower closed loop gain, but extended the bandwidth. The third point is we can modify input and output impedances. Modify input and output impedances. So we can see a normal circuit at the left-hand side. This is a common source amplifier. It's a common source amplifier. So at no load condition, I do not attach the blue color RL now. It should be negative GMRD. But if I have loaded it already, then the RD becomes a bit different. I have RD parallel with RL. So if loaded, the gain is negative GM, RD RL divided by RD plus RL. So in that case, we try to plug in the values. If GM is 0.05, RL is 1 kilo. So at the first case with no load, seems like my gain can be negative 50. But with load, my gain drops by half, which is negative 25. So looks like it is not so good. Okay, but if I add feedback, So I put my A over there, I add some K feedback circuit, and then I add the load outside of it. I add the load outside of it. So we said already the formula for gain is, for closed loop is A over 1 plus KA. So I just plug exactly inside, no load condition, A over 1 plus KA, 8.33. If loaded condition, remember my A changed to negative 25. So my A changed to negative 25, but overall, my gain drops by probably 1.13 like that on it. So it is very, very little. It did not drop by a factor of 2. It did not divide by 2. Comparatively, for the first case that it doesn't have any feedback. And lastly, before we go into all the topologies, is we have high linearity. With bandwidth, with closed loop system, with feedback system, we can have high linearity. For example, this is a differential amplifier. So initially, the differential output over differential input, it is the black color line. Okay, so let's say a closed loop gain, we say is equals to A over 1 plus Ka. So the closed loop gain is at point 1 maybe. At point A, it is 9.1. But at number 2, okay, so maybe at here, initially the gain is very high, so 100. So 100, it drops to 9.1, okay? But later on, when the closed loop gain maybe change to somewhere here, it is 50 already, but it drops by only a little bit, 8.33. So you can see the black color slope, it is very steep, but the red color slope is your feedback system. It is not so steep. So it is more linear compared to your original open loop circuit. So this part means that, oh, it can span for a longer range. It can accept a longer range of input, a longer range of output. So the whole circuit is more linear. Any questions so far? Okay, so let's look very shortly at all this sense and feedback network. So we say for a feedback model, we already draw this a few times. We already see this a few times. Generally, feedback model is just like this. But what exactly is the A? What exactly is the K? So the A, we can also model them into, instead of a triangle, we can model them into a rectangle. So A, the left-hand side of it will be the input, right-hand side of it will be the output. However, for K, you can see the symbol K, the triangle is inverted from A. So we can say that K actually receiving input from the right-hand side, K receiving output from the left-hand side. So you just need to remember this roughly. And the next thing you need to remember is, if we want to sense something, we want to measure, right? So remember the K is the multimeter. You can measure voltage, you can measure current. So the K is the multimeter. If I want to measure something, I want to measure the output of my gain, output voltage of my gain. So I have to place it in parallel, meaning that my K needs to place in parallel with my A, so that I can know what is the output of my A, output voltage of my A. And then, as mentioned earlier, if you are acting as a voltmeter, your resistance should be infinity, so that it doesn't draw any current by itself. Resistance should be infinity. So how you draw is, my A, my K, you just draw separately. Now my K input needs to measure the output from my A. There needs to be in parallel. Parallel means one hand connect to hand A, connect to hand A, hand B connect to hand B. So my top hand connect to top hand, bottom hand connect to bottom hand. And remember, this resistance should be infinity. Next is, what if I want to measure current? Measure current. So measure currents means the whole circuit should be in series. In series means that forms a loop. So you connect them this way. The top hand is at the bottom hand. The top hand is at the bottom hand already. And if it is ammeter, we requires a series circuit, we requires the resistance to be very, very, very low. So the resistance is 0. For return mechanism, so just now is we measure, but how do we feed back to the feedback subtractor? So we will subtract 2 voltage or current. We want to subtract the symbol here just now. It is basically subtracting X minus U. So similarly, we want to do the subtraction. Okay. So if you want to subtract voltage, we know that voltage, if we place in parallel, then there's no point, their voltage is the same. So if you want to subtract voltage, we have to place them in series. And remember now, my K I measure already, I want to feed back to my A. Now my K looks like a voltage source already. I am giving some voltage back to my feedback circuit. My K now is acting as a voltage source, so the resistance is supposed to be 0. Okay, ideally supposed to be 0. And then we can minus out we can subtract the voltage. So here, if you connect in series, basically V in, so this point is your U. We can say V in minus U is basically your input for your X, for your A. V in minus U is input for your A. But if we want to measure current, if you want to feed back current, so just now I measure voltage already, I want to feed back to current. So if you want to feed back current, we know that if current is series, the current is the same. So we have to place them in parallel. In parallel, meaning that first hand connect to first hand, bottom hand connects to bottom hand. And my A now, it will be getting, the input is actually I in. So your I in will just be whatever current flow from you. I in minus U equals to the input for your A. That's the general concept on it. Okay. So meaning that we can have different combination. We can sense voltage, return voltage. We can send voltage, return current. We can sense current, return voltage. We can sense current, return current. So there are 4 different combinations that we'll be looking at. Okay, so we can have probably a 7 minutes break before we continue to the next one. Okay, let's continue. So the first type of feedback network is I sense voltage, I give back voltage. So this is what we call a voltage sensing circuit. Okay, so we say voltage means my K input is voltage, my K output is voltage. So we are referring to what we are sensing and what we are feedbacking. The naming is a bit confusing, okay? But this circuit, another term, we also call it a series parallel, series shunt network. So you can see from my last table, we are sensing voltage, returning voltage. It's a voltage feedback system. We also call it a series shunt network. Series shunt network. So from left to right, we read the name series shunt feedback network. Okay, so how do we actually name that? We say that a feedback network generally, you don't see these two parts first. Generally, we got A, we got K. So the first thing we draw usually is just the A, the block A with two lines, input, two lines output. Then we will have the feedback K, again, two lines input, two lines output. What happens is, how do we make sure it is actually sensing voltage? Means my K want to read voltage. What do we do if my K want to read voltage? It needs to be in parallel with my gain. It needs to be in parallel with my gain block. So this is a multimeter now. K is a voltmeter now. So K in parallel means first hand connect to first hand, bottom hand connects to bottom hand. So it looks exactly like this. Now my K want to pass back voltage into my A. Pass voltage into my A. So it is a voltage is a voltage source now. I want to minus out the voltage sources. So just like I mentioned, if you want to minus voltage source, it needs to connect in series. So I connect my input in series. So my input now is basically V in. My K output from my K is K times V out. So what is my input to my A? Input to my A will just be V in minus K V out equals to this one, V in minus K V out. So let's look at closed loop gain. Now we formulate closed loop gain. Take note that we haven't go into transistor base. So closed loop gain, what exactly is your V out? We can say V out is equals to V in minus K V out times A, because it is just this input times A. So we rearrange, okay? We multiply everything inside. So you get V out over V in to be A over 1 plus Ka. So looks like the one that we derived earlier, A over 1 plus Ka. So that's your closed loop gain. The first thing that you notice, this is your closed loop gain. What? And then the next thing that usually you want to find in closed loop system is closed loop input impedance. Closed loop input impedance. How do we find input impedance? Since we say it is impedance, right? Input, right? So the resistor needs to be at the input. We said that V in, go in, the whole thing should be an ideal voltage source going in. But we know nothing is ideal. Since this is a voltage source, it's supposed to have some very small series resistor connected. So we draw this R in, additional R in out. Now our circuit change a little bit. Okay, this will becomes, you can see, we can say that this R in has a voltage of V equals to IR. So I in times R in. I in is what we don't know, but that's okay. So we know this part of it will have a voltage of I in times R in. So this voltage times with A1 becomes A1 I in R in. A1 I in multiplied by my K, it becomes K A1 I in output from here. So what happens now? When we say we want to find input impedance, it is V in over I in. V in over I in, because V equals to IR, V over I equals to R. We want to find out what is the R at input. So V in over R in now, you can model it. What happens is V in over R in. So we can see the derivation. We can say V in is basically now equals to I in R in this voltage plus this voltage, right? So I in plus with K I in. So these two voltage add up equals to V in. Since it is equals to V in, you can take out this I in. You can divide everything by I in. So put I in over here, cancel this I in, cancel this I in. You take R in out, it becomes this red color part. So that is the whole red color part is your closed loop input impedance. So it is very common to ask what is the open loop gain, closed loop gain. So for feedback, usually just want to find closed loop gain, open loop gain, R in, closed loop, then R out, closed loop. So those are the very common terms that we need to find. So this is your R in closed loop. But what about R in open loop? What is the small R in over there? This small R in is basically your open loop input impedance. This is your the small R in, the R in is your open loop input impedance. As for closed loop output impedance, we remain the whole circuit. But to find the output impedance in the closed loop, okay, we will need to model it a little bit. Okay, we will need to add a voltage source, because when we want to find the R out last time, we will apply a test voltage, ideal voltage source at the output. So now similarly, we will put ideal voltage source at the output. At the same time, we say that this A1 will give us some voltage. So the sum voltage over here, what exactly is that? It is a voltage source. So we have a voltage source, we have a resistor. So non-ideal voltage source over here. So this non-ideal voltage source is basically R out. So how do we find that? We can say that Ix, this Vx, ideal test voltage, you give you Vx, Ix, sorry. This current, what exactly is this current? So we want to find out what is the current, means we want to find out what is the V over R. So this current basically is Vx minus what happens at this point. So what exactly happens at this point? What exactly happens at this point? We can say this is your K, this is your Vx. Vx is in parallel to your input of K. So your K output is supposed to getting Vx as well. So this is KVx. So what is this over here? So this over here, take note that my to imply a test voltage, usually I will need to ground everything else. So my input is grounded. So if here I got KVx, up there I supposed to have negative KVx. So my amplifier will get a voltage of negative KVx A1. So Vx minus negative KVx A1 divided by R out. Then you get this equation. I just want to find what is my output impedance, closed loop output impedance. Basically, I want to find what is my Vx over Ix. So from here, you rearrange, you find out what is Vx over Ix. You get this whole term. This is the whole red color term is your closed loop output impedance. And the R out up there is your open loop output impedance. Okay, so we can summarize a bit. So for voltage, or we call it series shunt feedback. Your closed loop gain is equals to A over 1 plus Ka. Your R in closed loop, is equals to R in 1 plus Ka. Your R out closed loop is equals to R out 1 plus Ka. These are actually not meaningless. Okay, you might wonder, why do we need to find? So you realize that we say that the output supposed to have a very small impedance. After we derive, we realize that yes, R out is divided by something Ka. So this supposed to have very small output impedance. So that's correct. It makes sense. Input over here supposed to have very big impedance. So correct. It is in multiplied with something. So it is very big. So we derive this impedance is actually, they are somewhat meaningful. Okay. So let's see some example with transistor now. Okay. If I give you this circuit, what type of amplifier is this? What type of amplifier is this? Common source, common gate, common drain. It's a common gate, okay? Because the input is at your source or drain. Is at your source. Your output is at your drain. Gate is basically some bias current. So now I want you to check whether this is a negative feedback network or if it is a positive feedback network. And then we want to find the gain and we want to find the input-output impedance. Okay, we go through one by one. So to check if it is a negative feedback network, what we usually do is, you see this is a closed loop circuit. We are feedback what we out back to your we in. So this is a feedback network. What we can do to check whether it is negative feedback or not, we need to break the loop. So I break this loop. I know this is exactly where I need to break because usually I only have this part as my amplifier, but now I added R1, R2. So this is where I exactly need to break. I break the loop. I apply a test voltage. Negative feedback works as in, if my test voltage increases, my output decreases, then that's correct. So the point that you break, one part of it needs to be your test voltage. The other part of it is your VF, which is feedback voltage. As long as both of them are inverted, then that is negative feedback. Then we can continue analyze this circuit. If it is not, then we do need to do this already. So let's go part by part. If VT increases, what happens to the current? What happens to the V out? Okay, we can say that V out is over here. V out is basically VDD minus IDRD. So if your VT increases, this current increases, right? Because your gate voltage increases. So if current increase, then your V out decreases. So V out decreases. Here is just voltage divider. So VF automatically decreases as well. So now when VT increase, VF decrease. So yes, it is negative feedback network. So we can continue to analyze this circuit. Okay, I will pause here for a while. You have a look to check whether you really understand how you find negative feedback, positive feedback. Okay, now look at, just like I say, we want to find closed loop gain. want to check whether it's negative feedback. We want to find the gain of it, the closed loop gain of it, and input-output impedance. Okay, so this is a voltage feedback because here is voltage divider. We are getting some voltage, and then the output is voltage. It feeds back to the K. So we can say that this is basically the circuit that we learned, voltage feedback network. Just now we already derived for voltage feedback network. Our closed loop gain is fixed already to be this, input impedance to be this, output impedance to be this. So we just, now we want to find the closed loop gain of this. Basically, it will be very easy. So closed loop gain, we say it is exactly A over 1 plus Ka. So what is your A? A is your open loop gain. So this is a common gate circuit. If it is individual amplifier itself, common gate circuit is just A equals to GMRD. It doesn't have the negative because it didn't invert it. So it's GMRD. What exactly is your K? K is the feedback network. What are the components that contribute to feedback? It is R1 and R2. R1 and R2. So R1 and R2 act as a voltage divider. So we can say K is basically your R2 over R1 plus R2. So we can substitute inside already. We know A, we know K. So we know A, we know K, we substitute everything inside. Your input over output over input, your closed loop gain is equals to this one directly. You just substitute the values. For open loop input impedance, just now we say the formula is R in 1 plus Ka. So what exactly is your R in? Ka we already know. What exactly is your R in? R in means the open loop input impedance. So where do we see that? You see from your V inside input, what are the resistance that you can see? I mentioned many times already, from source to drain, we are seeing 1 over Gm as your resistance. So 1 over Gm is your R in, open loop input impedance. As for output impedance, we say that output closed loop impedance is R over 1 plus Ka. Again, Ka we got, but what exactly is your R out? R out is when you look at output, what are the resistance that you can see? Ideally, here is infinity, so you can only see Rd. So your R out is Rd directly. Okay, the next one, have a look. The other example. This example is a little bit special. We know the left-hand part is common gate because input is at the source, output is at the drain. But the second part of it is common drain because the input, my transistor is getting some input from my output, from my common gate. So input is from the gate, output is at the drain, at the source, sorry. But drain is the VDD. So this is common drain. What exactly is common drain, if you can recall? Common drain means that it won't amplify anything. It is basically just a buffer. The gain remains the same, almost the same. So we can say that now it looks like, or the output from my A, it will feed back to my common gate. Output from my common drain will feed back to my common gate, means nothing changes. So my A is still, my K is equals to 1. The feedback is equals to 1. So K is equals to 1. This whole thing is basically your gain, your open loop gain. So if you want to find closed loop input impedance, we say that equals to R in 1 plus Ka1. What is your R in? Input is still the same, 1 over Gm1. But what exactly is your K? K is 1. What is your A1? A1 is the whole thing. A1 is the whole thing. So it will be Gm RD because it's just a common gate times 1. The drain gain is 1. So it's just Gm RD. For closed loop impedance, you already got your K, you already got your gain, you already got output, R out. we need to find what is R out now. R out is this output. So this output is looking at the source of your second transistor. So it will be 1 over GM2. The last example for voltage feedback. So this looks exactly the same as this circuit. They are exactly the same. Okay, but I only added a CL capacitor over here. That's the only difference. So what if I want to find what is the closed loop bandwidth? Open loop bandwidth. Just now we only learned closed loop gain, input impedance, output impedance. What if I want to find the bandwidth? So to find bandwidth, the formula is closed loop bandwidth equals to open loop bandwidth times 1 plus Ka. So this is the thing that you need to remember. Open loop bandwidth times 1 plus Ka. Basically means that closed loop bandwidth will always be much higher than open loop bandwidth. And then open loop bandwidth, usually we say it is just 1 over RC. So closed loop bandwidth now will just be 1 over RC times 1 plus GMRD. So let's say initially this circuit will have only one pole. This pole is RD over CL. So this is the pole, output pole. I want to see what is the impedance, the bandwidth of it. I say is 1 over RC, 1 over RD over CL. But now I say I want to find closed loop bandwidth. So it will just be 1 over RDCL times 1 plus Ka. Ka is 1 plus GMRD. So that is modifying the bandwidth. Okay, the next, before we go to the next one, let's take attendance first. Okay, please take your attendance. There's 10 of you, so there's one more haven't signed. Who haven't signed your attendance? Okay, never mind. So the second type, so actually the only important one are these two feedback network. The other two is less, I don't think they are commonly used. So the important one are voltage, and voltage current. So we say it's a voltage current, meaning that my feedback is sensing some voltage. I feed it as a current back to the input. I feed it as a current back to the input. So we also call this a trans impedance amplifier. I get voltage, I let you know what is the current. So again, to know what is the connection, I will draw my A and draw my K first. But now remember, I want to measure voltage. My K needs to measure voltage. So my K act as a voltmeter to measure voltage. It needs to be in parallel. Now I say I want to give back current to the circuit. So meaning that I want to minus out current. When I say I need to minus out current, I need to make sure they are in parallel so that it can be minus out. So we have to place them in parallel so that my I in input, it can minus out whatever current from here. That's why you can see both are in shunt connection. So we also call them shunt network. Shunt feedback network. So it can be when we say current voltage, we read from right to left. When we say shunt, series shunt, we read from left to right. Okay. So let's examine this circuit a little bit. We can say that this amplifier, output is voltage, input is current, so it's V over I. So this gain is basically R. Then after K, it is always K V out. Over here, that's okay. And K is receiving, K output is current, K input is voltage. So I over V is just 1 over ohm. Okay, 1 over ohm. So we know that V over R is equals to current. Okay, V over R is equals to current. So you can see V out times with 1 over ohm. Basically, it's your current. So we feedback current inside. So this is the correct drawing for your shunt feedback network. Then we examine what is the closed loop gain. Closed loop gain. Generally, we say that closed loop gain, when we first derive, we already know it is supposed to be equals to A over 1 plus Ka. But just now, when we draw for this circuit, what exactly is the A? We say that this A is basically one resistor. So we change this A to be a resistor. We call it R0. So we can modify the whole circuit to be R0 over 1 plus K R0 directly. So this will be our closed loop gain. Okay, or you want to go part by part also can. We can say that V out is equals to A, so which is your R0 multiplied by I in minus KV out. I in minus KV out. So at the same, you multiply inside, then you also get the same thing, R0 over 1 plus K R0. So you can compare both of them, they're exactly the same thing. But if you want to find input impedance, so now slightly different. Input impedance, we say that output, you remain everything the same thing. But for the left-hand side input, since this is a current source now, this is a current source, we said that we always need a very small resistor at the front part. So we will draw a small resistor at the front part. So since we have drawn a small resistor at the front part, we want to know exactly what is your V in over I in. That is your closed loop input impedance. Closed loop input impedance. So now let's see. V in is the only voltage that will go into the circuit is this part. Can we say V in this voltage is equals to whatever current that flows into R in? The current that flows into R in, it is not just I in, yeah? Because I in go in, it will split into two paths. So it is your I in minus KV out, outside over here, KV out times R in, then it's only the current that flows into R in. So we can say V in equals to I in minus the output from KV out times R in. Then it's only the input voltage that going into the circuit. Then you can multiply. So what exactly is your V out? Over here. So we can multiply inside first. Okay, so we can say that, okay, so we take out this R in. And then we can say V out is basically equals to your R naught times V in over R in. R naught times V in R in. Okay, V times R. So V equals to IR. This R is your R in over here. Okay, so you can see V over R is your current. So this is I times your gain R naught. So V equals to IR. This whole thing will be your V out. V in over R in is your current. R naught is your gain. This whole terms multiplied will be your V out. So we can find what exactly is your V in over I in already. It is R in over 1 plus K R naught. So this is your open loop input impedance. Okay, over here, I'm just trying to eliminate out my V out. Okay, but that's still the same thing. You can say V out is equals to R naught over R in times V in. That's the same thing. Okay, we just want to get an output voltage. For closed loop output impedance, now we say that we do the exact same thing as just now. It's a voltage source. We apply a test voltage. Over here, again, we will have the gain times with in series with 1 R out, very similar to what we have done just now. So we know that this output will basically be negative K times your Vx voltage. Go back, multiply by R naught. Because here we ground it already. So it will be negative K, and then whatever voltage over here that comes in is V. Negative K Vx, and then my gain is R naught. R naught. So this becomes a source. It becomes a resistor, a source. Multiply with this R out, in series with this R out, sorry. So now this is your model for your closed loop output impedance. How do we find what is Ix? We say is Vx minus whatever at this point. Whatever at this point, it will be negative K Vx R naught. Whatever at this point, it is negative K Vx R naught. Divided by R out, it will be your Ix. So if we rearrange, we just want to find Vx over Ix, you get R out over 1 plus K R naught. Take note that R out is your open loop output impedance. R naught now is your gain, is your A basically. So it's still the same thing. You realize that R out is very small because we are measuring voltage. And then over here, now this is a current already. It's supposed to have very small impedance as well. That's why your closed loop input impedance, it is also something divided by 1 plus K R naught. It is also very small. So now let's look at the last. Okay, let's look at this example directly. This will be the last example for today. So how do we actually feedback? Just now we say we want to take voltage. It is very easy to take voltage. I can measure voltage easily. But how do I convert this voltage into current? So the question goes back to transistor. Remember, our MOSFET is a voltage to current converter. So we go back to transistor. We can just use only one transistor. My transistor and MOS, the gate connect to output, so I can measure what's the output voltage already. I measure voltage, but my input, my transistor output, I know that my transistor give output as a current. So this current drain I connect to somewhere, then I already feedback as a voltage to current converter. So let's find one by one. What is the open loop gain of this circuit? Open loop gain is whatever over here. This is a common gate circuit. This is a common gate circuit. Okay, basically I want to find out what is the V out over I in. V out over I in. Okay, in this case, can we say that Just now we already modeled this is the only resistor. So if you want to go through the small signal model, we can. Okay. But if you want to find out V out over I in, basically V over I is just an R. It's just an resistor. So we can just say that V out is basically equals to I in, because this I in is idea, right? It flows through the whole series transistor. So this RD will experience the same input current. So ID RD will be equals to your V out directly. I in RD is your V out. So first open loop gain we have found is basically equals to RD directly. Open loop input impedance. Input, we're looking from source to drain. So it is 1 over GM. Output, we are looking at RD only. Bottom is idea. So it is RD. Closed loop gain, just now we derived this rectangle part. So we just need to substitute everything inside. Basically, R0 is your open loop gain. So I substitute RD inside. R0 is your open loop gain, I substitute RD inside. But what exactly is your K? K is a current source. K is a current source. It converts the voltage to current. That is basically our trans impedance. So we convert. So it's basically output is I, input is V. So that is our conductance. Conductance is 1 over GM. That's why conductance is GM, sorry. That's why our K is basically just GM2 in this case. This is something that can convert voltage to current. Like your small signal model, you will draw GM VGS. So that's the GM of it. This transistor acts as a GM of it. So this K is just GM directly. If you want to find what is the K, you can still do that. Okay, we try out. Assume that we do know that is our GM. So we draw. This is the NMOS over here, M2, VGS, and then we know there's one ID. So I want to find out what is the ID over V out. When we draw this small signal model, we have a transistor like this. We have maybe the top part, bottom part we don't draw, but we will act this as a current source. So GM, VGS, and then this will be my ID. So I can say ID is equals to GM, VGS. But this VGS now is actually my V out. Okay, this is the output. This is my V out. So GM, V out. That's why ID over V out is equals to GM2. So we put K equals to GM2. Then the rest of it is just substitution already. This is what we have derived. This is what we have derived. So we just substitute all the values inside. R in is impedance looking from input. So 1 over GM. K we have found just now. R0 is your amplifier open loop gain. And the rest of it is the same thing. Okay, I think that's it for the feedback. The other two is less likely will be used. So this for sure won't be in quiz. I won't go through first. So I won't be seeing you guys next week. Okay, I will see you guys on week 12, Friday. That class will be important. I will be giving you your quiz scope, some revisions, and then we'll have our quiz 2 weeks later. So week 14, we will have our quiz. Is that okay? All right, if nothing else.